The facial expression recognition (FAIR) and action unit recognition (AUR) tasks have garnered significant interest in the computer vision community. Recent studies have proposed various deep learning-based approaches to achieve state-of-the-art performance. However, constructing effective positive-negative pairs for contrastive learning on facial behavior datasets remains challenging due to subject ID information and limited subjects. The proposed text-driven contrastive learning method, CLEF, addresses this issue by utilizing coarse-grained information and text-embedded labels. CLEF comprises two stages, both using a unified vision text architecture, CLIP. In pre-training, positive samples are from the same activity, and negative samples are from different activities. Activity descriptions are used as coarse-grained labels to guide weakly-supervised contrastive learning, minimizing intra-activity differences in representations. CLEF leverages activity descriptions to create positive-negative pairs, encouraging the encoder to focus on activity features rather than identity features. Cross-modal contrastive learning pushes image features close to textual features, enhancing the learning of better representations. In fine-tuning, CLEF adapts to both image and text scenarios, utilizing image and text encoders. The loss functions include self-supervised contrastive loss for name description pairs and supervised contrastive loss for image label pairs. The proposed CLEF model has been evaluated on 6 datasets, achieving state-of-the-art performance. This demonstrates the effectiveness of the proposed method in enhancing facial behavior recognition. The model's ability to leverage textual information in addition to visual data sets it apart from previous works. The experimental results show that CLEF can effectively alleviate the influence of identity variation and improve the performance of FAIR and AUR tasks. CLEF's main contributions include proposing a weakly supervised contrastive learning method, exploring the use of text-driven contrastive learning on FAIR and AUR tasks, and conducting extensive experiments on 3 in the lab and 3 in the wild datasets. The proposed contrastive learning for emotion and facial action unit recognition (CLEF) method jointly trains supervised contrastive losses for image-text pairs, utilizing prompt templates to augment original labels. The model architecture consists of a 12-layer transformer text encoder and a VITB, 16-image encoder. Pre-trained on BP4D and BP4D plus datasets using weakly supervised contrastive learning, CLEF is fine-tuned on downstream tasks with a combination of supervised contrastive loss and self-supervised contrastive loss. The evaluation metric for action unit recognition, AUR, is the averaged F1 score over all AUS, and for facial emotion recognition, FAIR, it is accuracy. CLEF achieves the best performance on BP4D and DISFA datasets, with an F1 score of 65.9 and 64.8, respectively. The method also outperforms state-of-the-art works on EffectNet, RAFDB, and FAIR Plus datasets. CLEF demonstrates its effectiveness in facial action unit recognition and facial emotion recognition, achieving outstanding performance on the BP4D Plus database and outperforming state-of-the-art methods in 3 AUS. The overall improvement is 1.4% compared to baseline methods. CLEF also achieves the best performance on average F1 score in terms of 8 AUS on the DISFA database. An ablation study evaluates the effectiveness of each component in CLEF, showing that using both label names and descriptions achieves the best performance. Visualizations of expression features and similarity matrices demonstrate CLEF's ability to enhance class separability and capture relevancy between image and text queries. The results demonstrate CLEF's generalization ability and effectiveness in facial expression recognition tasks. Here is a combined summary of the 4 pages. The paper presents a weakly supervised text-driven contrastive method, CLEF, for learning advanced facial representations. This approach leverages coarse-grained activity information to disentangle subject identity features and minimize intra-activity feature differences while maximizing interactivity feature differences. The method incorporates textual label names and descriptions to directly apply to facial expression recognition, FAIR, and facial action unit recognition, AUR, tasks. A graph autoencoder, GUI, is used to visualize the relevancy heat map between image name and image description pairs, demonstrating the text encoder's ability to extract semantic knowledge from label names. The heat map localizes corresponding regions of the face by querying the label name or label description. The advanced pairing method is activity-based, designed to elicit specific expressions, resulting in images with expression intensity ranging from none to onset, peak, and offset. The method can be easily extended by integrating intensity details into label names. The paper discusses limitations, including the reliance on prior knowledge of coarse-grained textual descriptions, the use of a fixed prompt template for label names, and variations in performance across OS caused by semantic descriptive writing. CLEF achieves state-of-the-art results on 3 in the lab databases for Taoyue and 3 in the wild databases for FAIR. Ablation experiments demonstrate the effectiveness of weakly-supervised contrast learning in pre-training and the validity of using textual information from activity, label name, and label description. The paper provides a comprehensive overview of related work in facial expression recognition and action unit recognition, citing various studies that have contributed to the advancement of these fields, including the development of novel architectures, attention mechanisms, transformers, and visual linguistic representations. The Weakly-Supervised Text-Driven Contrastive Learning for Facial Behavior Understanding framework employs a comprehensive approach to facial behavior understanding, utilizing both activity and label semantic descriptions. The activities in the BP4D and BP4D Plus datasets are designed to elicit various emotions, and the label semantic descriptions are divided into facial expression and facial action unit labels, based on psychology studies. The framework leverages pseudocodes for pre-training and fine-tuning, as outlined in Algorithms 1 and 2. The pre-training stage involves training a model using a vision transformer for images and a text transformer for text descriptions, with a supervised contrastive loss function applied to the scaled cosine similarities between feature representations. The fine-tuning stage trains the model on specific tasks, such as facial expression recognition or action unit recognition, using a combination of task-specific loss and label description loss. The authors provide implementation details, including hyperparameters and augmentation strategies. Text prompt templates are used to generate label name and description prompts, with a single template for label name prompts and 7 templates for label description prompts. The templates facilitate the generation of text descriptions for images, which are used as input to the text transformer. An ablation study on the hyperparameter lambda reveals that performance peaks when lambda is set to 2. Visualizations of prediction probabilities on the RAFDB dataset demonstrate the framework's effectiveness in recognizing facial expressions and action units. The authors provide a comprehensive description of the activities, label semantics, and pseudocodes used in the framework, ensuring a thorough understanding of the approach. Overall, the framework offers a novel approach to facial behavior understanding, leveraging contrastive learning and text-driven representations. The authors establish a foundation in facial expression analysis by citing seminal works by Ekman and Friesen, 1971, and Ekman and Rosenberg, 1997, which introduced the facial action coding system, FACS, for categorizing facial movements into action units, AUS. Matsumoto's 1992 study provided further evidence for the universality of contempt expressions. Building upon these foundations, the authors leverage recent advances in computer vision and machine learning, specifically referencing Xiang et al.'s 2021 approach that combines semantic embedding and visual features for facial action unit detection. The authors propose a novel framework that integrates multimodal features, including visual, audio, and textual inputs, to enhance the detection of subtle facial expressions. This multimodal approach is motivated by the understanding that facial expressions are often accompanied by corresponding audio and linguistic cues. The framework comprises 2 primary components: a visual feature extractor and a multimodal fusion module. The visual feature extractor employs a convolutional neural network, CNN, to extract spatial and temporal features from facial images. The multimodal fusion module integrates these visual features with audio and textual inputs using a graph attention mechanism, which captures the relationships between different modalities. The dataset used for training and evaluation consists of annotated facial expressions with corresponding audio and textual labels, designed to capture a wide range of facial expressions, including subtle and complex emotions. By combining these components, the authors aim to improve the accuracy and robustness of O detection, ultimately enhancing the understanding of human emotions and behavior.